Hello everyone, my name is Florentino and I am a data engineer slash platform developer at Binary Edge. For those of you who still don't follow our work, we are a cybersecurity company, and what we are trying to do is to we have built and we are constantly developing a platform that allows you to gather as much information as you can about services running on the internet. And then, while we can provide access to this platform so you can run your own scans, we also are building products and services on top of this data that we gather. When you have the volumes of data that we have, and when you want to build a data product, you have to think about a data architecture, allowing you to work with your data and to provide access to that data in several ways. So with that in mind, I thought it would be interesting to share a little bit of how we have built our own data architecture. What are the tools that we have, and what are some of the, I would say, pitfalls that we have encountered in our journey so far. So before you build a data architecture, you have to think about exactly what are you trying to achieve. So speaking for our case, we have data coming from several machines that are constantly grabbing information about services running on the internet. And we want to store that data, and we want to afterwards have the ability to query that data in different forms. Also, we want to be able to process that data, for instance, for reports about security and stuff like that. So with that in mind, we started building a small diagram of what we wanted to have. So as I said, we have several machines scattered all along the internet that we can call sensors, and they send that data to a data sink. That sink will send the data to a message queue. And then we want to perform some stream processing on the information arriving to the queue. And here we might want to do some real-time analytics, we might want to clean that data, and we also use this stream processing to store the data in several formats according to our needs. We can also return the clean data to the message queue, so we can provide direct access by an API so that our clients can access that data in real time as a stream. So with this in mind, we started looking at the tools we could use to build this. So the Apache Foundation has a broad range of tools directed to data. And on the basis of it all, it's Apache Hadoop. Hadoop was originally built by Google, and in reality is a package with 3 tools. The first one, the Mapreduce Framework, is a programming framework and model, which the basic idea is that you create small units of work and you distribute those units of work through several machines and then gather the results. It's a type of scatter-gather operation. Then you have AGFS, which is a distributed file system. And the basic idea is to allow high throughput of files and low latency, and of course high availability. And then you have Yarn, which is a resource manager that controls the resources that MapReduce and other tools can use for processing data. So the good thing about Hadoop is that it has great interoperability with many other tools that I will talk about later. It has great community, and it's very common to find performance issues, bugs, etc. And you have a great community there ready to help. There's a lot of people with lots of experience that you can use, and it simply gets the job done. So Um, in each of the tools that I'm going to talk about, there are always some aspects that I think that are important to mention because are things that we are always going back to. In the case of Hadoop and most of the tools that I'm going to talk, you have to really be careful managing the resources that those tools can access. You have to be careful configuring the timeouts. For instance, when your data grows, you might have to change timeouts for certain things, certain inter-process communications. And of course, most of these tools are based on Java and the JVM, so there's always problems with heap memory. Regarding AGFS, you also have to think about how your data is going to be replicated. So, for instance, if you have a cluster with many nodes, if one goes down, you have to guarantee that the data is always all there, accessible for whatever are your needs. So, talking about the message queue part of the earlier diagram, you nowadays have lots of tools for message queuing. But for this case, for this interoperability of tools inside the Apache ecosystem, we looked at Kafka, which is a tool that was originally developed by LinkedIn. The idea was to have a tool that is massively scalable and works in publish-subscribe fashion. It works with some really simple concepts. You have topics, which basically are the different queues that you write to. You have consumers, which are the clients. You have consumer groups, which are groups of clients, and you can use these consumer groups to basically distribute work through many consumers. And you have partitions and replicas that, well, are self-explanatory. Kafka is one of the tools that I like the most because it's one of the tools that gives me less work. Like I said before, as your data grows, you have to think about timeouts, you have to think about configuring message sizes, and one of the things you have to be most careful about is configuring retention logs and the cleanup interval. So you can configure how much disk space Kafka can use to keep information and how long to keep that information. And the thing is, if you don't configure retention logs and you have too much cleanup interval too big, you're gonna fill up all your disk space. So to tell you a story, we had a development cluster with a very large cleanup interval and no retention log maximum size configuration. So we filled up all the disk space. And someone had the brilliant idea, namely me, of I'm going to just delete the whole folder and we are all fine. And we are not fine, so don't do that. There are tools to clean up the queues. Because in reality what happens is that there is a tool behind Kafka that manages the synchronization between the nodes, which is called Zookeeper. And when you delete all the folders of the logs, what will happen is that you will create some inconsistencies that are very hard to resolve on Zookeeper. And then you won't be able to recreate the topics, to delete the topics, to do anything. The whole system turns to mush. So, you know, don't do that. Moving on, and this is the part that I like to talk the most, is stream processing. Nowadays, I would say there are three tools in the Hadoop ecosystem that are the kings of stream processing, which is Storm, Spark, and Flink. When we first began building our data architecture, we started with Spark. Spark is very simple. It has a very simple API. The functions that you encounter in the native API are very like any other function you would find in a normal, the standard libraries of a programming language. Stuff like map, stuff like filter, very simple things. And it has some other frameworks on top of it, like the data frame API, which is very similar to pandas. They're very nice to work with. and also has a very wide community, and it has lots of add-ons, which is the result of that big community. Now, for stream processing, this tool did not give me much happiness because I found it very hard to handle because it used a lot of resources and the performance we would get would not be that great. You have to constantly be careful with timeouts, and this uses a lot of memory. And the throughput I would get with, let's say, a 3-node cluster with a good kind of resources. I'm not going to specify, but assume that it's good. I would get like from 2,000 to 5,000 events per second. And for our case, this was a bit low, and we were incurring in several delays. Our kind of data does not need to be real time, but it's nice to have. And we were incurring in delays of 1-2 hours, if not more. So we started to look to other tools, and we found Storm. Now, Storm is not so simple to develop with. It's a very different programming model. While Spark is very natural to build, Storm is not. Storm, it works with bolts and spouts, where spouts are the, how can I explain it? Let's think about a network, a graph with several nodes. So Spark uses a structure kind of like that, in which each node does a small part of the processing. You have nodes which gather data or generate data, which are spouts, and you have bolts that do all the processing. And you have to build like a topology separating all these small parts of processing. And it's not as intuitive as Spark, but what we found out is that its performance is much greater for the kind of stream processing. We went from 2,000 to 3,000 events per second to, let's say, 300,000. I really don't know the upper limit we can achieve because we didn't reach there, but the maximum we've had so far was 300,000 events per second, which is a great difference. And the resource fingerprint of this is very low. In terms of memory, we would use like half of the cluster. We're talking about 40 gigs of memory per machine, maybe, I don't know, in Spark, and in this case, like 10 gigs of memory, which is it's a great difference of performance. I cannot stress this enough. When really for stream processing, once we went to Storm, we didn't never look back. And there's also lots of connectors, a great community. But then, just for the sake of keeping updated, we also looked for other tools, and we looked at Flink. Flink is not much used, does not have a great community, not as big, but tries to put together the best of both worlds. It has a great API, very simple, very similar to Spark, but it's also it's adequate for streaming. One thing I didn't mention but was in the slides, Spark does not have real streaming. What it does is mini batches, while Storm does have real streaming. You process one event per time. And Flink does that too. It's real streaming and has a very simple API. The performance from the very few tests that I've made, we didn't work much with Flink, but the very few tests I've made, the performance is not as great as Storm, but it's also, it's better than Spark, and that's not difficult. There's also another tool worth mentioning, which is Heron. So Storm was originally developed by Twitter, and eventually they thought, okay, let's change everything about the engine of Storm, but keep the interface, the main API. That's what they did, and they built Heron with that. It has very great performance, is much better than Storm. They say they can get up to 16 times better performance. I've yet to confirm this. But the downside is that you still don't have that great of a community. You don't have as many add-ons, as many connectors, many facilities as you would have with Storm, which has already been well developed by the community. But it's really, if you're interested in this topic, it's a really nice tool for you to keep in mind, for you to investigate. Talking about batch processing, you could use also Storm for this, but it's not an adequate tool. For this, I mainly use Spark because it's very simple to work with, as I said before. And, you know, batch processing does not have the same kind of problem that I mentioned before. You are not stuck with needing quick results. You just keep it processing, and when you get the results, you'll get there. And also, what I like about Spark is that you can have great tools on top of it that really make it easy for you to experiment with data, to test with data, stuff like Jupyter and Zeppelin. Basically, Jupyter and Zeppelin are, let's say, you can program and build a notebook with annotations, and you can program and see the results in real time. I should have brought an example, by the way. But it's really nice to experiment with data and to see the data in a nice format, and then it's already ready for printing if you need to output a quick report. It's really cool. Flink is also cool for batch processing, but again, it doesn't have that much of a great community, so most of the times you'll end up falling to Spark because it's easier. You will need to work with a certain tool that only supports Spark. The good thing about Flink is that it does have a better performance than Spark based on what I've seen. The thing about Spark, and I know I'm coming like a hater of Spark, but it's not like that. I really like Spark and I really use it much. But it really irritates me because it consumes a lot of memory, and as the tasks grow, you have to be really careful about what operations and the order of operations that you're using. You have to be careful about the resource allocation, about timeouts, and there's always something blowing up. Either driver memory, heap memory, worker memory. It's all kinds of issues. So, you know, yeah, this is what I've just talked about. But it's really a great tool. Talking about databases, here the choices are so many that I know we cannot cover them all. But before committing to a database, you have to think about what you want to do with data. Sometimes you just want to store, sometimes you want to have big query capabilities. So you need to think about that. When we were building our infrastructure for the first time, we were not thinking about having very advanced querying capabilities. So we searched for databases that could handle a big load of reads and writes. So we went to something like HBase. Thing about HBase is it has great performance for both writing and reading. But in terms of querying, you can only like fetch one record, fetch a set of sequential records. You cannot perform much querying on certain fields. For instance, if you have a JSON, it's not adequate for data modeling, it's just for storing. As the time would pass, we started thinking, okay, now we do need to perform some querying, so we migrated from HBase to Cassandra, which is a bit more advanced and it does have some nice querying capabilities. But it still doesn't allow you, for instance, to do advanced text search or anything like that. If you do need advanced text search, then you need to search for something probably outside of the Hadoop ecosystem. There are plugins for Cassandra to allow you to do advanced text search. plugins based on Solar and Lucene, if you ever have heard of that. But do not use that. From our experience, what we've noticed about these tools is that while Cassandra itself has a great performance in both querying and reading, writing, when you add this kind of add-ons, what happens is that you lose all the performance. You have the machines always hitting 100% of the resources, and it's really bad. And there's no, it doesn't compensate. You know, there are better tools for this. Now, you could install all of these tools on yourself without any management, without nothing. But then it would be really difficult for you to know when the services are running well, when you have to change configurations to propagate those configurations to the cluster. And there are lots of problems. When you have to make updates, you have to go to each machine individually. It's very sucky. So what we found out is that there is a tool also from Apache, which is Ambari, and it's great. It's the best thing ever. Apache Ambari has two parts. You have the server and we have the agents. The agents will be the machines of your cluster. And with the server, you can control the machines. You can choose in which machines you install what, and you can install everything from the server. You can configure all the machines of the cluster through the server. You can propagate the configurations to all machines, and you can configure everything on the fly, and it's propagated immediately. So there's not that you use that worry that the configurations were not equal in all the nodes of the cluster. You can also keep track if all the services are running. You have monitoring. You can configure alerts. It's really great, and it really eases the job of someone managing a cluster like this with many services. Ambari uses Hadoop ecosystem distributions. What this means is that there are some companies that create distributions using, they basically compile a lot of tools of this ecosystem in one nice little package, and Ambari uses these packages to install this in a cluster. The good thing about these packages is that the versions of the tools that I provide are already well tested, and you know they will work with each other. So sometimes when there's a new version of one of the services, you may think that you should update right away, but what happens is that most of the times that new version will break compatibility with some other tools. So when you use some of these distributions, you are escaping of that, because if a new version of the distribution is launched, probably is because the new versions of the services were tested and are working well. So revisiting the earlier diagram, we have the sensors, we have the data sync. The data sync will send the data to Kafka, which is our message queue, and then we will process it in real time with Storm and store it in a database, whichever it is, and a GFS, our file system. We will also return a clean version of the data to Kafka so that it can be consumed by an API, so that our clients can access that data in real time. Then if we want to build a report based on historical data or something like that, we can use Spark. Now, this is all very nice, but in reality there's, when you have a small team, like our case, there's a lot of overhead. You lose a lot of time managing the cluster, performing maintenance operations, configuring. You lose a lot of time on this. So there is something to be said about cloud services. The advantage of using cloud services is that you return the focus to the product, basically. You will not need to spend your time with complex configurations, with maintenance, guaranteeing that everything is up and running. And you can focus on data, making your analysis, building your products. The downside of cloud services is that they are very expensive, some of them. So for our case, what we find that is worth is to measure which services we could use, which services make sense to send to the cloud, which services don't make sense and we are better off using our own configured machines. So using Google as an example, you can substitute those services that I was talking before, all by Google services. So in the case of Kafka, you can use Google PubSub, which is a publish-subscribe service. And you don't have to worry about memory, timeouts, or anything like I've said. You just have to create your topics. You need your clients connecting to those topics, and that's it. There's not anything there to configure, and it just works, and it scales. For stream processing, you have Dataflow. Dataflow is not the direct match to Storm. It's really, you can configure a flow of data, you can configure how the stream is going to behave, but underneath it still uses Spark, although it's in the cloud. So if you have the money, you can scale that and actually achieve great performance. You have Google Cloud Storage, which is kind of like a GFS, is a distributed file system with great performance. You have Google Dataproc, which is an Hadoop cluster. You can create Hadoop clusters on the fly and do your analysis with Spark, with Mapreduce if you prefer. And you have databases like Bigtable or BigQuery. To give you an example, in our case, we use very much Dataproc because it's very easy to, when you need to do an analysis, you just boot up a cluster, you send a provisioning script with all the packages you need there, and you just start working. And when you're done, you just dispose of the cluster, and that's it. And it's not too much expensive. For instance, Google Bigtable, that's a very expensive service. So in this case, we thought, okay, we are better off keeping our own database. It's just that service. We can migrate to other things. Just to finish, you also can do the same with Amazon. There's also great services on Amazon. The difference that I've found between Amazon and Google is that while Google have a simpler, it has a very low number of services. The services are very simpler to use, but Amazon, it has some more years of experience there. So, while it's more complex and you have a more broad range of services, you also have a different type of security. So basically this is what I've wanted to talk about. I wanted to not to take much of your time, but to show you what tools you could use to build your own architecture and what were the common pitfalls that I found. In particular, when I talk to someone out there about stream processing, they always talk about Spark, 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 and I'm always like, no, why are you using Spark? That didn't work for me. Why are you? And so I thought it would be interesting to show the perspectives that that we found when we were doing our own thing. So this is more or less what I wanted to talk about. If you have some questions, please go ahead.
Hi.
Hi.
Apache drill could be used in this architecture in some way?
So you said Apache Beam?
No, drill.
Drill, yes. Apache Drill provides a very nice interface to handle with data. You could use this on top, for instance, of AGFS. So you could easily query, like it was SQL, raw files. In our case, we have lots of files with JSON data. You could use drill to perform SQL-like queries on top of those files. The thing about drill and most of the tools like drill, I think there is also Apache Phoenix and some others, is that those tools are mostly formatted for similar to tabular data. So if you have a structured JSON with lots of levels, drill won't do the trick, because sometimes you need to perform aggregations or do some calculations using very nested fields, you see, and drill won't work for that. Drill will take the JSON and assume it's a table and won't be able to work well with the levels. So you could use it, but it doesn't work always. So there's always that in mind.
So if I have, for example, a lot of CSV or JSON files as the input, it's better to put in a message queue and go to Spark?
If you have a lot of CSV, you probably won't have any problem using drill, because CSV is like a table, so that works well. For JSON, it depends on the schema. You see, if you have a simple schema like 1, 2 levels, it won't be a problem. If you have lots of objects inside of arrays, inside of objects, etc., drill will not work, and you're better off using, for instance, Spark. Now, Spark can connect directly to AGFS, and you can load the files to Spark, and you can filter and map. You can do normal operations that you would do in any programming language. You can load the JSON data, you can select the fields, filter this, segregate that. I find it a lot easier to use Spark and create my own scripts on the fly than to use a tool that is not very adequate for the kinds of data that we have.
Okay, thank you.
Hello. Does any of the streaming tools that you presented deal with back pressure or something like that?
Sorry, could you repeat?
Does any of the tools that you presented deal with back pressure? For example, if Kafka is sending messages too fast, is there any way for you to tell Kafka to, okay, drop some messages or try to send them slow, or if you're reading from a file?
Yeah. It's completely possible. When we use Storm, for instance, you have frameworks inside Storm that allow you to perform real-time analytics, and you can filter data, you can rate limit data, you can manipulate data however you want. If you want to slow it down, if you want to aggregate small parts of it, you can do all of that. One thing I didn't mention, nowadays Kafka already includes tools to process the data. So you can do all of that, and pretty much all of the tools will allow you to do that one way or the other.
Okay, thank you.
Thank you.